Hello and welcome to the Open Heat Transfer course Conduction. This course is brought to you by RWTH Aachen University and the University of Twente. My name is Wilco Robes, and in this video we will look at the semi-infinite body solution for conductive heat transport. The learning goals of this video are as follows. First, we would like to understand and apply the correct boundary conditions for the semi-infinite body where we impose a wall temperature. Afterwards, we will look at the solution of this problem using the error function or a tabled value of those. In the second step, we will look at a boundary condition with an additional thermal resistance on the outside, which changes the solution slightly, but still applies a similar approach. Now, let's look here in our categorization of the different problems. So in the previous lecture, we have looked at the homogeneous case, and now we look for a case where the body temperature inside is not homogeneous, but also where the temperature has not penetrated fully through the body. And this will lead us to the semi-infinite approach. And today we will look here at a constant temperature and as well as a convective resistance on the surface. And of course, we are working still in a one-dimensional approach. So, what is a semi-infinite body? As mentioned here, the temperature variation in a body depends on the location and the time. So, T is a function of maybe 3 locations and the time. But for the semi-infinite case, the temperature change on the right side here is negligible, so that the plate thickness is not an influencing parameter for the problem. We see here now that the wall here on the left side, a heat flux is entering this wall, and that the temperature here at the surface is giving us T1. And we also see that the initial temperature of the body, so for any location T equal to 0, the temperature is T0. So in the first case, it's a step function here on the surface. Now, with time, the temperatures increase, and we can see this here in the yellow and orange part. The next part, or the next graph in time, would be the red one, where now the temperature on the surface on the right side here has also significantly increased. But we will limit our approach to the yellow and the orange part where the temperature has not severely changed here on the right side. This is an assumption of the semi-infinite body, and on the red curve here we see that this assumption is not longer valid anymore. If we compare this now to a thicker wall, we can see that the yellow and the orange curve are exactly identical. So the thickness of the wall has not an influence on the solution of the problem. And here, for the thicker body, also at the time for the red part here, for the red graph, we have also a valid assumption of the semi-infinite body. What we see here is that the semi-infinite body assumption is valid for small times, meaning that the temperature has not penetrated through the wall, or for very thick surfaces. We could even imagine the surface of the Earth, where due to summer and winter there is a penetration of heat going in. So this could be a solution, or bodies who have a very bad thermal conductivity. Also for those bodies, the time in which this assumption is valid can be quite long. So finally, let's summarize. This boundary condition here on the right side is for T larger than 0, so after the initial change of temperature, always T0, and this is exactly identical to that the temperature at x equal to infinity is equal to T0. Now, how does the differential equation and the boundary conditions look like for this problem. So first, the differential equation. We had this a few lectures ago already, so we can write it in a dimensionless form with a dimensionless temperature difference T minus T0, so we have the initial condition here, and TA minus T0, so it's a jump in temperature here. And due to the fact that we introduced the parameter theta, we have a jump from 0 to 1, or vice versa. The initial temperature is here 1 at the surface, the initial temperature here is 0, and we have to describe this temperature jump over time. The influencing parameter here is the A, and that's the thermal diffusivity, which is equal to the thermal conductivity divided by the density and the heat capacity. Now, looking at the differential equation, we see that is second order in space and first order in time, which means that we need one initial condition and two boundary conditions to solve this problem. So what type of initial conditions and boundary conditions can we use? Let's first start with the initial condition. So at T equal to 0, inside our plate here, from 0 to infinity, so through the entire plate, the temperature is equal to T0, which translates in the dimensionless temperature to a value of theta equal to 0. As a boundary condition, we can apply here on this side that for T larger than 0, at location x equal to 0, the temperature is our temperature TA, which then translates to the dimensionless temperature of 1. Now, the other boundary condition we will use here on the right side, but not at the plate thickness delta, but at the location x equal to infinity, which is now again a justification for our semi-infinite problem. And here x is equal to T0, which then translates again that the dimensionless temperature is equal to 0. Now, how can we connect the two coordinates? We have one spatial coordinate and we have a temporal coordinate. And now we use a way to give a new parameter. We introduce the parameter eta, which connects the spatial parameter x with the temporal parameter t. And with this definition of eta, we are able to transform this differential equation, which has two different coordinates, to a differential equation only depending on eta. How can we do that? So first of all, we have to replace this d theta by dt. And to replace this, we expand it by d eta divided by d eta. And on the right-hand side, we have the d eta divided by dt. And we can, of course, take the derivative of that part here with respect to the time, and we come up with the prefactor of x divided by the square root of 4at by the power of 3. That comes due to differentiation of the t, and then times the value d theta d eta. For the other equation here, we have also to replace this. I would like to refer here to the end of the video or to the end of the presentation. There are more information on the derivation of this equation. Here, if we take the second derivative of eta with respect to x, we can see here first derivative is a constant, second derivative is 0, so the entire term drops. And the other part is that we have to take the first derivative with respect to x and then make integrate this, multiply it by itself, and we come up with 1 over at. Now we can replace this differential equation now, so we can introduce here the part that we had here on the bottom. On the right side here, we replace it by this part here, and if we transfer those values back, then we can replace this, the square root of x divided by square root of 4at. It's exactly eta, so we can place eta in front of this part, and here the a, the thermal diffusivity, cancels out, and the t cancels out with the t by the power of 3 and their square root of that, So we are left with the following equation. How can we proceed with this equation? Of course, we have to solve it. And for solving now, we do the next mathematical trick. We make a substitution. So we substitute d eta star divided by d theta divided by d eta. We substitute this with variable z. And so dz after d eta is equal to the second derivative of theta star divided by eta square. That's the derivative. Now if we take from this equation here the derivative, now we can replace this part here. We want to, at the end, we want to replace this and this with z. So the equation here, dz over d eta plus 2 eta times z is equal to 0. So this is a reference to this equation, just replacing the eta, but the theta by z. And we can solve this equation by the separation of variables. We see here we have put variables depending on z on the left side, the variables depending on eta on the right side, and that the next step is the integration of this equation. So integrating the left side will give us a logarithm of z, and integrating the right part will give us first the eta square plus then a constant c1. So we can explicitly write z now as the theta star d eta, and so we can also use, if we integrate, if we take the exponent of ln z and the exponent on the right side, we get here the right side of our equation. And this, because we have an exponent of c1, we can replace the exponent of c1 also by c2. That's an equation for z now. Now, in order to utilize the boundary conditions in order to get a solution, we integrate our equation on the left side from theta star 1 to theta star 2, d theta star, and the same on the right side from eta 1 to eta 2. So what is eta 1 and eta 2, and what is theta star 1 and theta star 2? For this, we use our boundary conditions. So we had the first boundary condition on the left side, where for t equal larger than 0 at the location on the left side x equal to 0, temperature is the environmental temperature, and so this theta star is equal to 1. What is eta for this value? X equal to 0 translates then to eta equal to 0. The second boundary condition is for x equal to infinity, but also t larger than 0. To what translates this? We see if the x is equal to infinity, eta is also being infinity. So for eta being infinity, the temperature T star is equal to 0. Now with these two boundary conditions that we can enter in this equation, we can obtain a solution. So on the left hand side it's easy. It's just the integration of 1 d theta star, and so we have the differences here between the two dimensionless temperatures. And on the right side here we have now to integrate our equation from 0 to infinity of the exponent of minus eta squared d eta. This is a little bit more complex. I don't know it myself, so what I will do in order to identify a solution of an integral, I will use Wolfram alpha, and Wolfram alpha as a very powerful tool for integrals and differential equations. It will give us that this integration here from 0 to infinity is equal to the square root of pi divided by 2. So here just shown how I put this into Wolfram alpha, and Wolfram alpha will give me the value for that. So now we have the solution C2 is equal to minus 2 divided by the square root of pi. The next step is to write our equation. The dimensionless temperature independence of eta is equal to 1 minus 2 divided by pi, square root of pi, that's the C2, and then 0 to infinity to eta of the exponent of minus zeta squared d zeta. This is now the next step. We have to integrate that. and the integral of this equation is the error function. So instead of writing this term, we can also write that the equation here is now the dimensionless temperature is equal to 1 minus the error function of eta. How does the error function look like? The error function starts at for eta equal to 0 at the value of 0 and then approaches the value of 1 after a short time. But it's just asymptotically approaching this value. Now, the temperature behaves like 1 minus the error function, so it's the inverse function here. We can see that we start here at the value of 1, and then we are decreasing in our value for larger values of eta. We don't need to use your computer to calculate the error function. There are tables here in the appendix of our formulary, book of formulas, and we can see here for different values of eta, it gives us the value of the error function. Now, as a little example, we will look now at which position x in our semi-infinite plate the temperature, dimensionless temperature, has reached a value of 0.01 after 10 seconds. The value of 0.01 is small, so it means that there's a slight change in the temperature, and now the question is how thick can the plate be until which we have a change of the temperature. It's like a 1% increase of the temperature compared to its initial temperature. So we know that the value theta star of eta is equal to 0.01. This is what we are looking for, and we also know that this is equal to 1 minus the error function of eta. We are looking at the value of eta, so we put this on the other side, know that the error function of eta should have a value of 0.99. Looking in the table will tell us that the error function eta with a value of 0.99, this is nearly 0.99, is then equal to 1.8. So the value of eta is 1.8, and now we have to translate this value of eta to a dimensional coordinate. How do we do that? We know that we have changed eta. This parameter is equal to the length x divided by the square root of 4at. We know the time 10 seconds, and now we need the properties, and with the properties we can then calculate the thickness x, or the location x at which the temperature has been raised by 1% compared to its initial temperature. Now let's do that for two different properties. So on one side we use copper with a very high thermal conductivity. Also the thermal diffusivity is very high, and we see that if we plug in all those values, the location is 0.123 meters. So the heat has penetrated 12 centimeters into the material after 10 seconds. For paper with the lower thermal diffusivity, here it's a few orders of magnitude lower. We see that the penetration depth is only 4.3 millimeters. So there is a severe difference in the two materials, but we can see this also here because the thermal diffusivity is in the square root. So we could have, in order to obtain this value, we could have also just compared the square root of a for the same time, of course, than with the square root of a from the others. So it would be easier to make a comparison. For this, we don't need a time and we don't need a location to have a comparison of the penetration depth. Now, the thermal diffusivity determines the speed with which a temperature information propagates in a body. This is an important characteristic of a body, and that's a quantity that we use here for our reference. What we have looked at now was the constant temperature case. In the next step, we would like to look at the case what happens if there's an additional convective resistance. What does change? So we have the same differential equation, we have the same problem, We have also the same dimensionless temperature difference, but now this part here is not constant anymore. So there is not a negligible heat transfer resistance, but a severe heat transfer resistance on the outside as well. And so for times larger than 0, our temperature will decrease here on the outside. So we have a convection on the outside, a convective resistance, and we have on the other side a conduction inside. So we have a convective resistance and a conductive resistance that determine the problem. What are now the boundary conditions if we are at a time t larger than 0 here at the location x equal to 0? The boundary condition is a balance between convection and conduction. So the conduction inside the object is always equal to the convection outside the object, and the convection outside is referenced by the difference between the ambient temperature and the temperature at the surface. And of course, the conduction is depending on the temperature gradient at the surface and the thermal conductivity of the material. So the boundary condition will be of third kind, meaning that there's a relation between the gradient and the absolute temperature T at the surface. In dimensionless form, we can also write this boundary condition, and then it becomes a little bit simpler because this term here is a part of the definition of the dimensionless temperature, and we see that the dimensionless temperature gradient at x equal to 0 is minus alpha divided by lambda. And this is also one important part or reason to introduce this dimensionless temperature, because now we have a constant and before we had a third type boundary condition. So from the first step, for the first boundary condition, we are now sure the second boundary condition remains untouched. So at x equal to infinity, we have the temperature T at theta star is equal to 0. And the initial conditions are also the same as in the case before. Now, how can we determine the temperature gradient on the wall? And for this, I would like to introduce now a little graphical solution approach. So let's look here at our case. What we have here on the left side is a convection, on the right side the conduction, and here it's a surface. If we have a look at our boundary condition here, then this boundary condition relates the gradient to the temperature difference. If we can rewrite this boundary condition, and we see that this alpha divided by lambda is in its units 1 divided by meter. So the flipping this value, lambda divided by alpha, has a unit of meter and is a spatial difference between the temperature TA and the temperature T surface in order to describe the temperature gradient here. So how can we do that? Now, if we put here in our diagram or in our graphic, lambda divided by alpha, so this meter, this distance here, if we draw that here, and we also draw the temperature difference TA minus a T at the surface, Tx equal to 0, this location, we get a gradient, and this gradient here, which you can now draw with a dashed line, is equal to the gradient that we have here inside our material. So the temperature drop from the inside the gaseous phase here on the surface is from TA to T equal to the location x equal to 0, and on the other side we have the gradient inside the material, and of course due to the often lower thermal conductivity in the gas or in the liquid, the temperature gradient here, as shown in the red part, is larger than the temperature gradient inside the material. So that was just a graphical way. Let's now go back to the boundary conditions that we had. So we had the boundary conditions here for the location x equals 0. We had the boundary condition for the infinity part, and we had the initial conditions. What can we do now? We had, for the case without severe heat transfer resistance, our solution looked like that. We have the dimensionless temperature is being 1 minus the error function of the parameter eta. And so we can rewrite this here, because what we see here, x divided by at, or square root of at, is just a Fourier number. So we can express this also in the dimensionless Fourier number, with the Fourier number is equal to a times t divided by a coordinate or length scale L square. And one other dimensionless number that describes our problem here is, of course, a Biot number, because we have the two resistances. One's the outside convective resistance and the resistance of the material with the thermal conductivity. Now, for alpha being not equal to infinity, we have a slightly more complex equation. I don't want to go into the derivation of the equation in detail. So we see that instead of having just a dependency on the Fourier number, we also have dependency on the Biot number. And from that, we get a little different equation, but being at the end the solution. Now, instead of using the equation to calculate the temperature inside the body, we can also refer to different diagrams that show the values of theta star depending once on the combination of Fourier and Biot. And this combination is exactly the important part, because we can see here it's Fourier times Biot square. So taking the square root of this, we have the square root of Fourier times the Biot number, and also here it's Fourier times Biot. Now, the different values that arise here can be seen if we have, for instance, an infinity value, which just means that, for instance, the heat transfer coefficient alpha is infinite. So this is exactly the same as we had before, the case alpha equal to infinity, where we have no thermal resistance at the outside because the temperature at the surface is equal to 1. This is the case for alpha being equal to infinity. Now, a little example. We are now looking at the position at which the dimensionless temperature eta has reached a value of 0.2, and that after 10 seconds for the material of copper. How can we do that? So first of all, we need to calculate this value with square root of Fourier times Biot, and for that we use the values given, and we come up with the solution that the value is equal to alpha, the value of the heat transfer coefficient, which we have not specified yet, times 8.53 times the 10 by the power of minus 5. So this is the value for the first dimensionless number, and now we can look into our diagram and do some calculations with that. We are looking at the value, or seeking for a value eta, or the dimensionless temperature, equal to 0.2. So we can draw a line here on this part, and then we can consider two different cases. So the first case that we had before is that the thermal heat transfer coefficient on the outside is infinity. So we impose directly the wall temperature. For this, we can now look into our diagram and see that this curve here intersects with the value of 0.2 at a location eta approximately equal to 0.85. With this value, we can directly calculate the penetration depth, which is now equal to 0.058 meters, so 5.8 centimeters. For the next case, we look at the thermal resistance, and let's start here with a value of 0.3. The value of 0.3 will lead to a heat transfer coefficient of 3.5, which is severely not that high for this case. So there's a relatively bad heat transfer on the surface, maybe just due to natural convection. So for that case, we have eta approximately equal to 0.2. And with this value of eta approximately 0.2, we can go into our equation of x equal to eta square root of 4at, and calculate again the penetration depth, which is in this example now 1.36 centimeters. So the penetration depth is much lower. But we can also see from this diagram here, which shows the temperature profile, that the temperature drop from 1 to, let's say, maybe 0.35 here, it's very much inside the gaseous or liquid phase instead of inside the solid phase. Now let's compare the solutions with the arrow function and the diagram. Finally, we had looked at the case where eta is, or theta star of eta is equal to 0.2. So the value here, then if we use the arrow function value, we are looking for the arrow function value of 0.8. Let's do that. The arrow function value of 0.8 or 0.797 is 0.9. So eta in this case is 0.9. From our readings, we had 0.85, so there's a little difference. And with that, our penetration depth x here is equal to 6.15 meters. As mentioned before, from the graph, we had the value of 0.85. That's from reading. And so there's a slight difference in the penetration, but this is due to a slight reading inaccuracy. And I think it's quite fair because it's not so easy to read this diagram. So the values are quite close to each other. With that, I'm finishing this pretty long and complex video. And I would like to finalize it with 3 questions. So what is meant by a semi-infinite body and how is it defined? So the important part in case of a semi-infinite body is that the temperature information has not penetrated through the body. And that means that the body is either thick or the body has a relatively low thermal conductivity. And from that, we can calculate then the penetration depth. And if the penetration depth is lower than the body thickness, then we, of course, save with a semi-infinite body assumption. Which two-dimensional numbers describes the transient temperature profile within a semi-infinite body with a relevant convective resistance? So as soon as we see a body and we have heat transfer inside the body, conduction, and a thermal resistance, a convective thermal resistance on the outside, and we compare these two resistances, we have directly the Bio number as a relevant parameter. The other relevant parameter is a Fourier number, which is then a scale for the time of the change and the information transport due to the thermal diffusivity. What is meant by the thermal penetration depth? So the thermal penetration depth is the depth until which the temperature information has been penetrated in the time given. So usually a value of, let's say, 0.99 is assumed. So the question is, at what location has the temperature been changed by 1% up to which the, and this is then the definition of the thermal penetration depth. Thank you for your attention and see you in the next video.